Hi, everyone. My name is Nick. It's my absolute pleasure to be here with you today to do a deep dive on the work we did on using AI to help build the fastest possible boat for Team New Zealand in the last America's Cup. I'm the chief data scientist for QuantumBlack in Australia. QuantumBlack is the advanced analytics arm of McKinsey. And before I go into a technical dive on what we did, I thought I would start by playing a quick video summarizing our work.
The America's Cup Match 2021. This is a big race. Magnificent flying machine.
Here we go, here comes the push.
The fastest boat wins the America's Cup, and we're seeing that right now.
Emirates Team New Zealand do it again in a new class of boat that proves Kiwis can fly. Sailing's most treasured prize, the America's Cup stays in New Zealand.
The America's Cup is the oldest sports trophy ever.
Got a lot of history there, and at the same time you're blending all that history with just cutting edge technology.
Most people think of what we do as we go sailing. Well, we do, but it's not sailing. We go low flying aircraft sort of on the water with great hydrodynamic and aerodynamic qualities.
The technology and the design can really make the difference between winning and losing.
You have a simulator that's completely repeatable. You can model the same weather conditions, the boat going through the same waves. However, to drive the simulator, you've got to have sailors involved in that. And they're out on the water, and so to actually get the right people together is a real challenge, and the sailors are not completely consistent.
It was something that was really cool when McKinsey came in, as they really challenged us and gave us a lot of new ideas and ways of solving solutions that we probably perhaps hadn't thought about before.
What we were trying to achieve was incredibly difficult, and I was quite sceptical. We started off by getting the agent to learn how to sail in a straight line, upwind and downwind. The crucial moment was when it all of a sudden started doing upwind times and tacks and jibes that were better than the sailors were doing in the simulator.
That was a good moment, and that was the point where I was like, yep, we've got something here that is going to be useful.
I don't think we're the first team that's thought about AI. Difference simply is that with working with McKinsey, what we now have, which is pretty unique and pretty advanced, probably doesn't exist in these other organisations.
Designers can iterate through foils in a much quicker way. What typically would take a day or several days, they can run through in a matter of hours.
Sailors, as athletes and as competitive people, wanted to ensure that there was nothing to learn from the bot, and they don't want to be beaten by a computer.
The bot does so many runs, and to be able to go down there and compare what you're doing with the bot is where we see the performance gains.
AI in this case, that's the future. If you haven't got good AI within a few years, you're not going to be on the page.
So, as you saw in the video, the boats that are now sailing in the America's Cup are those fairly amazing flying machines. I don't want here to go into all the details of what the America's Cup is and how exactly we used AI, but I'll invite you to watch the keynote again if you want to do that. What I wanted to focus on here is more around how we used AI for design. And so if you think about the design process for such a complex engineering system, it's always very iterative. And so what we're trying to do here is speed up the rate of iterations by fundamentally removing humans from the loop where we can. Not in full, but to at least make sure that then humans are only in the loop when they need to be. And so with that premise, really what we wanted to do is build an autopilot for their boat simulator so that you could evaluate new design at speed in ways that had never been done before. And when you think about doing that, there's many different ways you can think about it from a operational research perspective. I'm not even saying machine learning here, because machine learning might not always be the right option. And so it's always interesting to first think about, okay, well, here's the problem I want to solve. Here are my different options on how to solve it. And so that's what the team on the ground had done. And they had managed to solve this problem in a straight line with more traditional optimization techniques. But they couldn't make it work across a whole lap of the course when the boat actually has to turn and do a lot more dynamic maneuvers. So that's why we came for. Just to set the scene here, this is a really complex problem. You've seen probably, obviously, a lot of self-driving cars using all sorts of algorithms to drive. And two things to understand here. The first one is that here we're not driving a car, we're driving a boat, and that's intrinsically a lot more complex. It takes 3 to 5 people to drive a boat as opposed to just one human in a car. So that's the first thing. Second thing is it's a highly variable environment where your engine, which is the wind here, is always changing. So you can't rely on constant power or known power to actually control the boat. The other thing to understand as well is that when you're building a self-driving car, you will emphasize safety first, and performance will always be second. Here, in a very controlled environment, we're going for maximum performance. And that's also where a lot of the challenges are. It's maximum performance in a very repeatable way. And that's where making this work with machine learning was complex. You would have probably understood by now that we decided to tackle this problem with reinforcement learning. It was at the time when we first thought about it more than 18 months ago, not a very widespread approach to take a commercial simulator and try to put reinforcement learning on AI on top of it. And that's usually because those simulators have never been built for that purpose. And also because the problem we're trying to tackle here was extremely complex from a dynamics perspective, and also very loosely defined. You know, when you apply reinforcement learning to a video game or a board game, you have very clear rules about what playing well means. For us here, it took a lot of time with the sailing team, with the design team, to actually land on what this meant, and then attempt to teach the system how to do it. So with this setup, we obviously had a fairly traditional, at least from the outside, a fairly traditional reinforcement learning setup where you have your traditional agent on top here, interacting with an environment, which in our case is a simulator. Think of the simulator really as similarly to a plane simulator or any other type of like first-person simulator where you feed in some controls. In our case, they're all for software, but in practice, the sailors do it with hardware controls to a simulator that will then take those controls and then compute based on those controls and on the environment what the new state of the boat is. So the new position and the velocity and the acceleration. And doing that in a way that you also output a reward that will obviously tell the agent how well it's performing. And that reward is done in such a way that the agent is optimizing the velocity made good, which is the speed at which the boat is traveling towards the target. This is important to understand because the boat actually never travels straight towards the target. It always zigzags depending on the wind. And so with this premise, I want to now really spend the rest of this presentation deep diving on the technology choices, on the algorithm choices, and a lot of the issues that we had to solve to make this work. So obviously, this is the race summit. So we're going to start with the race stack here. And I want to show you first how we iterated. I mention it because quite often you read papers where they only show you how things work. But here I want to really take you through the whole process to actually make this thing work. First thing we had to do was adapt the commercial simulator to a reinforcement learning task, which in practice meant taking it from an on-prem environment to the cloud by fully virtualizing it and encapsulating it in a gym environment, which was in itself quite a lot of engineering, not so much machine learning, but obviously a lot of engineering to make this work. Once you have the simulator in the cloud, the first thing you want to do is figure out how you're going to learn on top of this simulator. I'll come on the next slide to the different types of algorithm, but what we settled on ultimately was a custom version of SAC where we could control a lot of the internal parameters, including managing the replay buffer and really initializing the whole system to suit our needs. And given how simple and efficient reinforcement learning is, obviously you want to be doing this in the cloud. And so in our case, that meant a bunch of instances managed on Ray and leveraging preemptible instances in the cloud, with all the problems that come with that around losing your workers and how you recover to still keep learning. For us, that was the only way that we could do it from a cost perspective, so that the team could actually use it at scale to design their boat. And so once you've solved all this problem, this is a machine learning problem, so you'll always have a range of hyperparameter to tune, whether it's the network architecture or whether it's the time horizon over which the agent is actually making decisions. And so that's where tune came in really handy to manage that. But even once you've actually tuned your system, you're never done, and you're constantly experimenting, trying new things, bringing on board the feedback from the designers, from the sailors. And so really keeping track over months and months of how the system developed, what performance changes we made over time, what changes to the configuration we made over time, becomes actually a really complex task. And so it's something that I would argue you need to think right from the beginning to get right, to have all that experimentation framework sorted out, because it's not something that you can necessarily change too many times along the way. Once you've done that, then you want to be validating with the end users that what you're doing works. I won't talk too much about the performance here, but only to say that we had to match the performance of the Olympic sailors in the simulator. And just let me tell you, they sail this boat amazingly well in the simulator. Like any quote unquote normal sailor or non-sailor like me doesn't stand a chance in the simulator when you're competing against the Olympic sailors. So getting to that level of performance is actually a real challenge. Beyond performance, then obviously you want to be controlling for variability. Making sure that if you evaluate the same fold multiple times, you actually do get the same result. Otherwise, you can never build the trust for the system to actually be used by the designers. And finally, thinking about the generalizability and how often you need to train your system, how far can you extrapolate when you think about the performance of new designs. So all those things need to be taken into consideration. And again, look, you never get it the first time right, and you need to iterate multiple times. But once you've done that, then you can actually design the system and feed in different shapes for your hydrofoils and rank them, and then change some parameterization and do the whole thing again. And that's what ultimately enables you to build a boat and race it. So that's the very, very short version of the story. If we deep dive now into what happens in practice, again, look, I don't want to go into all the different types of reinforcement learning you could try to solve this type of problem, but using this this well-known framework, I would say we're definitely on the left-hand side here, which is interesting because actually you have the exact physics model of the boat in the simulator. So you might think of, oh, then we actually have the full model. Why don't we use it? And in practice, what happens is that that physics model, that physics engine that fundamentally just solves partial differential equations in real time to really compute the interaction between the solid, which is the boat, with the water and with the air. This is just way too complex. And so you don't want to be building a system that would leverage that actual knowledge. So what we did was actually treat that physics engine as a black box and use a model-free approach. We first started with PPO, which actually worked pretty well, but obviously was very sample inefficient and took a very long time to converge. And so moving on to more Q-learning solutions, ultimately we landed on SAC. Main reasons being the sample efficiency through the off-policy learning, and also the way you can really control the trade-off between exploitation and exploration to actually find the best policy. We found that this was the right setup. As I mentioned previously, we actually did our own custom implementation. That's because at the time we couldn't find a version that could do what we wanted. Fundamentally, we looked at how to initialize the system, how to build the right curriculum, how to manage convergence, and I'll come back to that in a second. But first, I also wanted to show you what happens when the system doesn't work. And so here is just a typical example of the agent actually trying to sail the boat, thinking that it's doing some clever reward hacking by still accumulating rewards when obviously it's not at all sailing the boat the way it should be. And so all this to say that especially when you use an industrial simulator that was designed to do something else, as you use it more and more, you really make sure that you have the right reward function, and that you also quickly identify any potential issues with the simulator, because otherwise, obviously, the agent will be learning the wrong policy, and you will have a suboptimal control ultimately. And so really the learning here for everyone trying to do something like this is focusing on the right reward function and really building the tools to really be able to instrument and monitor that reward function. I say this because by the time you've put everything in a Docker container in the cloud at scale, it can actually be really tricky to go back and really understand what's happening in your system. And so building it in such a way that you can also run things locally and literally go step by step through it is extremely helpful. I mentioned earlier the stability of the system and the robustness. Obviously, that's usually one of the main drawbacks with reinforcement learning. It's very fiddly to use, and in a lot of situations, not always as robust as you would like it to be. And so I can't, unfortunately, share everything we did to make it work. But in broad terms here, we spend, obviously, a lot of time thinking about the right algorithm. A lot of time on the reward function. I mentioned it on a previous slide. I'll mention it here again. The reward function is basically the only way you have to bring in external knowledge or prior knowledge from your subject matter experts into solving the problem. And so you should absolutely focus on doing that, given the complexity of the task here. And the last thing I mentioned here is that when you do off-policy learning, there's a lot of things you can also do on your replay buffer to not only speed up the learning, but also make it ultimately more stable. And so the highly redacted graphs on the left-hand side here try to illustrate what I'm talking about. Think of the top one as an evolution of performance as you train your system. So it starts with pretty low performance, and then it actually figures something out. But as it keeps looking to improve it, the performance will drop and then come back up and then drop again. And so fundamentally, depending on when you stop the training, you run the risk of stopping in the wrong, in a state where the system is actually suboptimal. Compare that with what we ultimately managed to achieve in the bottom graph, where sure enough, the system takes a little bit longer at the beginning to learn, but when it actually starts learning, it quickly converges to the optimal performance and then stays there. And that was the really important thing in order to build trust in that system, is making sure that you really minimize the variability. Remember, the two things we're solving for was being able to do this at speed, but also with minimal amount of variance. And so that's what, it's this type of graph that then can convince the end users that the system is actually working. But having a system that works is not enough. And so you also want to really look at how you're going to use that system. And that's important when you have really complex reinforcement learning algorithms where any retraining involves quite a large amount of compute and therefore cost and time. And so what we looked at was over the entire design space, and here it's just parameterized across 2 dimensions, but you have to understand it's obviously much more complex, is trying to understand how generic our agent was and how it could optimally learn to sell a range of designs, and then use that information and knowledge to sell new designs optimally within a certain region around the designs that had been used for training. And again, I really emphasize here the fact that the performance has to be optimal no matter whether it's in training or testing, because if it's not, the designers can't use the tool. And so we build a system to pick the right designs to use for training, and build some bands, if you want, empirical bands in that case, around what was doable to use the system in practice. Obviously, you can't have a single agent, and so as you move through the design space, you also retrain another agent to be more specific to that part of the design space. But ultimately, that's what really, again, enables you to leverage reinforcement learning by managing the times and the costs through the generalization of the learning. So here's a quick video of what actually happens. So here's our agent optimally controlling the boat in the simulator. Here it's going in a straight line. And so as I said before, this could have been done with more traditional optimization techniques. But in a second, you'll see it turn. And those turns where actually you don't even see everything here, obviously, and it's heavily redacted. But a lot of things need to happen in a very specific sequence for the boat to optimally go around the turn. And so that's what the agent managed to learn in addition to going in a straight line. So that's what ultimately enabled the agent to do a full lap in the simulator. And once it could do a full lap, we could then compare the performance with the sailors. And again, look, we got to a point where the agent could actually match or exceed the performance of the sailors across a large range of conditions, which was by no means obvious when we started, as you saw in the video. And so with this tool, then the designers could then completely change the way they thought about iterating through their design process. And by removing all the uncertainty from the human inputs, but fundamentally by being exposed to a much wider range of the parameter space, and therefore increasing the likelihood of finding the best design. I want to spend more time now just a bit more on the technology and then on the key learnings. I've talked about a lot of the things on this slide already, but I think fundamentally when you try to solve a problem like this, you definitely want to be standing on the shoulders of giants. By that I mean using the highest level APIs possible and native services where possible as well, both on the infrastructure level, but also obviously for the pure reinforcement learning. And so doing that means that the team then focuses only on the value-adding tasks that have not yet been commoditized. In our case, reward shaping, maybe curriculum learning, experience replay buffer management, and the likes. And the important thing as well, when you do think of this over a long period of time, is making sure that you actually maintain that environment so that you can reproduce previous results. And as I mentioned as well, make sure you have the right way of managing your experiments to really close that loop so that you know what to do next. And that's tricky because those experiments might take a day or two or maybe more. And so as those experiments are running, someone in the team is already trying something new. And so making sure that all those innovations actually pull the boat, if I may say, in the right direction, is actually really complex. I want to conclude this presentation on sharing some of those learnings, again, across a whole range of dimensions. I've just mentioned the design and tracking of experiments. I will emphasize it again. I think finding the best way of managing your input config files, tracking your output metrics, having the right way of diagnosing and then debugging your problems is going to be time very well spent over the course of such a project. From an algorithmic perspective, I think obviously you want to be focusing on sample efficiency and convergence. But the interesting thing to keep in mind as well is, especially by the time you use preemptible instances, is thinking about how the algorithm you've chosen will be able to be checkpointed and restarted as your instances come online or offline. And we found that obviously some algorithms are easier to manage this way than others. Again, from a reward perspective, you really want to be focusing on bringing as much human priors as you can into your system, and also making sure that you can debug things so that you avoid any discontinuities or similar problems. From a simulation perspective, obviously you have to be anticipating bugs in your simulator. The agent is actually amazingly good at reward hacking and at finding issues either in the simulator or in your reward function. The hard thing is to know where the bugs are coming from. And finally, in terms of orchestration and hardware, having access to the best level of control of resources in a heterogeneous cluster is what makes those type of problems achievable. That's all I had for you today. I hope you enjoyed it, and thank you very much for watching.